Alrighty, so we are now on chapter 6. So this would be material that's going to be on exam 3, not the one next week, but in a couple weeks after that. We're going to be studying intermolecular forces now. So what we talked about last week, were what we call intramolecular forces. So last week we did intramolecular forces. And these were things like ionic bonds, covalent bonds, etc. Intra means within. So these particular forces are going to be forces that happen within a molecule. So you're just looking at one molecule, you see it's sharing some electrons, that's a covalent bond, and we can talk about properties of that bond and all that. Now, this week, we're going to talk about, or rather, this couple of days, we're going to talk about intermolecular forces. And inter means between. So we're going to be now looking at what happens when multiple molecules are interacting together. So we're going to see how do molecules interact. Just so you know, often we abbreviate this as IMFs, even though intramolecular forces also would fall under that same kind of abbreviation. We don't really talk about intramolecular forces as much. We just talk about covalent bonds or ionic bonds. So whenever I'm going to be saying IMFs, I mean intermolecular forces, okay? And so we're going to see that there is a relationship in physics that we can talk about here. In physics, we can talk about the force of attraction between two charged species being some constant. I'll explain what all these terms mean. We're not going to actually use this equation in this course, but it's important to understand what all this means. So this means that attractive force depends on Q is the charge of a particular species. So if we're looking at how two things are interacting together, we're looking at the charges they have. So if they have full charges, they're going to be very attracted to each other. If they have partial charges, they're going to be less attracted to each other. So Q1 and Q2 are just the charge on the two things that you're looking at. Again, we're not going to use this equation, but it's important that we understand how these factors are going to be relating together. And also on the distance between them. And that would be down here. That's the radius or in between them. So if we assume that things are spherical, it's the radius of like how far they are. So ideally, what we would have for a very strong attractive force highly charged small particles. That's kind of what you're looking for if you want to kind of maximize your attractive force. So the more charged you are and the smaller you are, that's what's going to get you to the biggest kind of attractive force. So when we're looking at how molecules are interacting with each other, if they're attracted to each other or not, that's what we're looking at. We're looking at basically how big the charge is on them, and we're also looking at kind of the size a little bit. So we're going to see that by and large the size is a harder one to mess with. Mostly we're going to focus on charge here. So aside from fully ionic interactions, we're going to see we have a number of ways of having not fully charged particles interact. So for example, yesterday let's take a look at some of the molecules that we did yesterday. We did Cl2 yesterday. We saw that its Lewis structure was the following. And we saw that because of the difference in electronegativity, we saw that overall kind of this side of the molecule was a little bit negative, and this side of the molecule is a little bit positive. And remember that within a molecule, the partial charges, they depend on the difference of electronegativity, right? So whatever that happens to be, I think for this it's going to be about 0.5 or so. So on the smaller side of polar things, but that's okay. We're going to see that if another SCl2 molecule comes in, it could come in two possible ways. We could have it come in like this, or like this. And so we want to kind of take a look at what's going to happen here. So if we have the molecule on the right interacting with it, remembering that overall we kind of had that negative side there, positive side of the molecule here, we're going to see that this is not going to be a favorable interaction here because negatives don't like to be near other negatives. However, if we look at the other molecule, the one on the left, we see we have a kind of happy interaction now, where we can have these partial positives and partial negatives interact together. And so we're going to see that that is an attractive force. They're charged things interacting with each other. This is not, again, going to be a super strong interaction. Nothing near the level of an ionic bond like sodium and chloride put together. But this is still going to be an important force. This is going to dictate some of the physical properties that sulfur dichloride will have. We call this particular interaction, let's write it in black, why not? This is called a dipole interaction. So, hopefully the name is not too crazy. We have two polar things interacting. And remember, polar things have dipole moments that we talked about yesterday. We're going to see that any two polar molecules will experience dipole-dipole interactions. With each other. And we're going to see that this is going to attract them to each other. And we're going to talk a little bit later about kind of ramifications or consequences of what happens when molecules are attracted to each other. But suffice it to say right now that polar molecules will be attracted to each other through these dipole-dipole interactions. All right, and so again, this is kind of what it looks like. We have a partial positive and a partial negative interacting together. So just so you know here, that's a partial positive and a partial negative attraction. All right, so probably the easiest case for our methods of interacting together. Any questions on that one? So just so you know, this stuff is going to apply to polar compounds only. All right. Alrighty then, in that case, let's go to our next one if there's no questions. So, our next one, we're going to see a special case of dipole-dipole interaction. And we're going to see that this one will involve hydrogen. So, if we take our absolute favorite molecule, water, and we can bring it with another water molecule, perhaps. Understanding again that the oxygen being more electronegative is going to be our negative part of this. And our hydrogens are going to be the positive part of this. And then we kind of have the same idea here for these. And we can see we can have this kind of very nice interaction happening. And so we're going to see that because hydrogen is very small and not electronegative, that means that the difference in electronegativity is generally large when hydrogen is bonded to a nonmetal. And because it's so small, another water molecule can get really close to a different water molecule. The hydrogens being so small allows those waters to get really close together. And if we go ahead and take a look at our equation before, we saw that the bigger the charges and the closer you can get them, that's what's going to maximize your force, your attractive force here. So we're going to see that because hydrogen is small and because it's not electronegative, we're going to see that we can get pretty big partial charges on the hydrogen. We're going to see that when hydrogen is covalently bonded to oxygen, nitrogen, or fluorine, we have something called hydrogen bonds. Here, I'll spell it out. Hydrogen bonding occurs. And we're only looking at hydrogen that's connected to one of these three elements because these three are all relatively electronegative. Actually, not even relatively. They're absolutely electronegative, right? Fluorine is our most, oxygen is our second most, nitrogen is our third most electronegative element. So we're going to see that between those, we're going to see something called hydrogen bonding happening. And this is just going to be an extra strong dipole interaction. And we see that it's extra strong, again, for two reasons here. Because hydrogen is small, molecules can get close. And because hydrogen is much lower, the partial charges are large. So we're going to have kind of supercharged things not fully charged, but kind of really strong partial charges here, and they're really small, so they can get close together, and that's going to really create a nice strong force for us. And we're going to see for all the forces that we're going to talk about, kind of this time, hydrogen bonding is going to be the strongest one. So hydrogen bonding is going to be much stronger than plain old dipole-dipole interaction. So dipole-dipole is anything that's polar. Hydrogen bonding is a special case of dipole interaction. So we still have dipoles in these molecules, and they're still kind of interacting together, but because hydrogen is so small and electropositive, we can get these to really interact strongly together. And we're going to see that hydrogen bonding is extremely important in biology. We're going to see that proteins and nucleic acids are all held together mainly through hydrogen bonds. Here, let's take a look at some of these things. What shall we look at? Let's take a look at some... Is this going to be... No, that's not the right screen. Okay. Let's take a look at some important aspects here. So, what we're going to see here is... Perhaps you've read about your base pairs in DNA. Actually, this looks like a pretty good, nice, large photo. Maybe not. What we can see here is we have covalently bonded hydrogen to nitrogens here, and they're interacting with oxygens or other nitrogens in other bases of DNA. We're going to see that's the reason that we have base pairing happening in DNA. It's these hydrogen bonds that are holding it all together. So you can see again on this particular one, I know it's a little bit smaller, but we'll live with it. We have an oxygen and a hydrogen covalently bonded. That hydrogen, being delta positive, is able to interact with an oxygen on another molecule. And the same things are happening down here. And so we're going to see it's a super important part of holding DNA together is these hydrogen bonds. And we're going to see in proteins, it's going to be much the same case. So in proteins that are made of amino acids have nitrogens and oxygens in them that have hydrogens. And we're going to see that those will interact with other protein molecules, or even protein molecules for the same protein just really far away from each other. And that's going to create perhaps what you've heard of as alpha helices and beta sheets that really hold proteins together. And I know this one's a bit more complicated, but you can see in 3D that hydrogen bonds are going to be allowing these molecules to really fit exactly where they should be fitting in proteins. And so proteins are very, very complex molecules, right? They're hundreds, thousands of atoms. But hydrogen, oxygen, and nitrogen are very important components of them. And we're going to see that those hydrogen bonds are going to be a very important part of holding things in the correct place. And if things are in the right place, they're going to behave properly, and we're going to get the good interactions there. So hydrogen bonds are going to be super, super important for biology. So, chances are if you end up taking biochemistry later on, you're going to see that the answer for a lot of things is going to be hydrogen bonds. So just understand that. So if we want to look at what can undergo hydrogen bonds, it's any molecule that has hydrogen bonded covalently to oxygen, fluorine, or nitrogen. Let me fix covalently here. Doesn't look like a C. There we go. So we're only looking at hydrogens that are on one of these three elements. If the hydrogen is on a different element, it cannot hydrogen bond. So if we look at methane, two methane molecules, we are not going to have no hydrogen bonding here for several reasons. First of all, the CH bond is considered non-polar, so you don't even have partial charges to deal with. But also, the hydrogen is on carbon here, so it cannot hydrogen bond. Even if one of these was now an oxygen, this hydrogen, let's make it a green hydrogen. This green hydrogen can only with other nitrogen, oxygen, or fluorines. So even if you have one molecule that has something that can hydrogen bond, like that hydrogen is bonded to an oxygen, so it is capable of hydrogen bonding. But for these intermolecular forces, you need a partner. You need to have two molecules, right? So there has to be something that has an oxygen, nitrogen, or fluorine for that hydrogen to interact with. So this hydrogen cannot interact with methane. But let's say if we had formaldehyde instead, now these two can interact together. Now we can see that that hydrogen can interact with that oxygen. So that's kind of what we're looking for here. So not only do you need it covalently bonded to an oxygen, nitrogen, or fluorine, but you need another molecule that has one of those three elements as kind of the bonding partner. So we're looking at kind of two things here. So we can have a hydrogen bond that exists in this scenario, but not one with methane. Methane did not have any oxygens, nitrogens, or fluorines, so we're not going to see any hydrogen bonding between methanol and methane. Methanol is the molecule on the right here. All right, so just again, I'm going to summarize. We can have kind of hydrogen bond donor, as we sometimes call it. That's the hydrogen on a fluorine, hydrogen on an oxygen, hydrogen on a nitrogen. And then an acceptor is going to be any other of those three elements. So if you really want to be correct about this, of course, two HF molecules can have hydrogen bonding together, right? That's great. We can have that happening. We can see that two HF molecules will definitely hydrogen bond. This one is going to be donating the bond. This one's going to be accepting. The accepting part is going to be the negative. The donating one is the positive side that's interacting together. So we're going to see that this, they can be the same molecule. That's not a problem. But if you're looking at two molecules, two different molecules, and you're asked if those two can hydrogen bond together, you have to look at if one of them can act as a donor, meaning it has the hydrogen that's bound to one of those three elements, and one of them has to be the acceptor, that it has one of those three elements. Doesn't matter if there's hydrogen on one of the other elements. Doesn't matter for the acceptor. The donor has to have hydrogen. The acceptor does not need to, but it can. Doesn't matter. Okay? So I'll just write that. Can also have H, but not required. So your acceptor can have hydrogen on it, but it doesn't need to. Alrighty. Any questions on the hydrogen bonding? Okie dokie. So, in that case, we're going to go to our last one, which are going to be called London Dispersion Forces, also called van der Waals forces. They're the same name. I usually say London Dispersion, but you might see both of these names further on in chemistry, so they're the same thing. And so we're going to see that anything with electrons can undergo this. So anything that has electrons, which is all matter. So everything. Everything can do this. However, it's kind of easiest to talk about it in terms of two atoms interacting together. So let's take a look at some xenon atoms. Xenon, if we take a look at our periodic table, has 54 electrons. It's got quite a few. It's a big atom, relatively speaking. It's still a noble gas, so it's relatively small compared to other things in its row, but of course, compared to something like helium, it's much larger, right? So if you imagine you have 54 electrons zipping around in their various orbitals in here. So electrons are kind of randomly distributed. Right? So the more electrons you have, we're going to see that the force will become stronger. So at a given time, you might see something like this. However, at another given time, you might end up with something like this, where just randomly many electrons kind of happen to be on one side of the atom. Just randomly. So they're all moving around. And so just for a fraction of a second, very, very short period of time, they might just happen to all be on the same side. Or you might just happen to have a lot of them on one side. If that's the case, you end up with a very, very small negative charge there. Very, very, very small. Just by the fact that all those electrons are on that side of the atom, so it just is a little bit more negative than it normally would be because all those electrons are just kind of over there. And as a result, the other side of the molecule is just a little bit positive. So we see this when I do this double delta, that means like partial of a partial. Which means super small. So a very, very small charge can happen there. But, I mean, that in itself is whatever. But what's really cool is this can induce other atoms to do the same thing. So if we have our atom here, this other atom, who might have its electrons all over the place, will be like, oh wait, there's a negative charge here. I'm going to actually end up moving some of my electrons away from that negative charge. And as a result, now this atom is now partially got a negative side to it and a partially positive side. So we can induce, that means to force it to happen, a very, very, very small dipole. So just because one atom happens to have electrons more bunched on one side, it can convince another atom to do the same thing. Just by having a very, very slight negative charge, it's going to push the electrons away in the next atom. And so as a result, you can induce or create another dipole in another atom. That's very, very small, not a huge dipole. All right, so these are very, very small. They're not permanent either. These are just going to be instantaneous dipoles as well. They don't last long. These are fractions of a second. So, microseconds, nanoseconds, femtoseconds, picoseconds. These are just tiny, tiny, tiny bits of time where this can happen. However, when it does happen, we saw before that when we have a positive and a negative, they can interact together, and that can be an attractive force. However, we see that this is much weaker than a dipole-dipole interaction. Because dipole-dipole has permanent partial charges. Whereas when we're looking at London dispersion forces, they are transient. Transient instantaneous partial charges. Transient means they go away quickly. So permanent charges are going to be better. Of course, you can have stronger attractions if they're permanently partially charged than something that just has an instantaneous charge that's going to go away in a little bit. However, we do see that everything can do this because everything has electrons. So we're going to see that these London dispersion forces get stronger the more electrons you have. Oops. What the heck? What is happening here? Oh dear, we are going back in time, everyone. I'm not sure what's happening. Alright, let's just save this and let's come back to it because things are... Oh no, we don't need to be on this one. Okay. Let's try this again. Maybe we won't have weird things happening. Okay. Back down we go. So, more electrons you have, the stronger your London forces become, just because the more electrons you have, the more chance there are to kind of gather on one side or something, or to make that charge a little bit stronger. So, we're going to see that with nonpolar molecules, their attractive forces depend entirely on molar mass. Why the heck are we talking about molar mass? Well, remember molar mass is your number of, protons and neutrons, right, essentially, for all the atoms in your particular compound. But that also means the number of electrons, right? So protons and electrons are typically equal, especially for compounds. They have to be neutral, right? So we're going to see that the more molar mass you have, the more electrons you have. The more electrons you have, the stronger your London forces become. And so we're going to see a couple of trends here. So if we pop over to the Google again, let's see some trends that we can get with something called alkanes. So let's go ahead and have a look at some charts here. So where's a nice chart for us? Aha. Okay. So if we just look at this, here I'll try and zoom in a bit. This lovely chart of molecules, which is now super small. That's helpful. Oh my goodness. So while these are not terribly in, these are alphabetically organized, so it kind of sucks. Okay, fine. Let's go find a new picture. This one's terrible. Go away. This is not the one I want. Okay, let me zoom out here. Okay, let's go with this one. So if we look here, we can see the chemical formulas for a couple of simple hydrocarbons. And we're going to see that we have a trend in boiling point or melting point. It's all going to work together. We're going to see that the bigger your molecules get, the larger your boiling point becomes. We're going to look at why that's going to be in a little bit. But this is just illustrating how, as your molecular mass, your molar mass increases, you're going to see that these London dispersion forces get larger and larger and larger. So notice this hexane here, C6H14, 6 carbons, 14 hydrogens, only has a boiling point of 69. Interesting. We know that our good friend water, so I'll just write that down, that hexane has a boiling point of 69 degrees. That just water here has a boiling point of 100 degrees Celsius. And if we look at the molar mass, let's see, this is going to be a molar mass of 86 or so grams per mole. The molar mass of water is 18 by comparison. However, we know that this hexane, C6H14, can only do London dispersion forces. However, our water can also do hydrogen bonding. And we're going to see that because hydrogen bonding is a much stronger attractive force, even though it weighs so little, it'll still have a very high boiling point. So let's finally talk about this boiling point stuff. So we're going to see that in chemistry, in order to break any bond, whether it is an intramolecular bond or an intermolecular bond, energy must be added. And so we're going to see that the boiling point, which is the energy for, or rather the temperature at which a liquid becomes a gas, we're going to see that this is proportional. Wow, I can't spell that. Proportional to the strength of intermolecular forces as a result. So we're trying to break these bonds so that things can become gases. When liquids are all very close together, right? They're attracted to each other. They're all moving around together. In order to become a gas, though, it has to break away from all the other molecules. Remember, we talked about gas molecules being super far apart. And so we're going to see that we're going to need to break those intermolecular forces if we want to become a gas. And so, unfortunately, we must go a little bit into physics again to talk about how temperature works with kinetic energy. So it's graph time. So this is temperature, which, remember, is related to kinetic energy. That's energy of motion, how fast things are moving. And we're going to see that we have, oh my goodness, again, this proportion word that I can't spell. Proportion. We're going to see that at a given temperature, let's just call this one kinetic energy. This is at a given temperature. At some given temperature, we're going to see that a certain number of molecules will have a certain energy. So kinetic energy and temperature are not exactly the same thing, but they're very closely related. And so we're going to see that maybe this amount of energy is what's needed to break the intermolecular forces. Let's just say. If we go to a higher temperature, at higher temperature, we're going to see that we shift this graph to the right a little bit. And so as we go with higher temperature, we have more molecules that have higher kinetic energy, and those are going to be more likely to break out of their intermolecular forces. And eventually, if we keep increasing our temperature, we're going to completely break all of our intermolecular forces. At that point, we'll have reached the boiling point. So we have enough energy where all the molecules basically have sufficient energy to kind of get out of there. And so we're going to see that we're going to be talking about a lot of properties related to this throughout this chapter. So, essentially, again, you don't need to be able to duplicate these graphs or anything, but understand that at higher temperature, more molecules will have higher kinetic energy, and therefore are more likely to break intermolecular forces. And so if you want to think about this kind of visually, we have our water molecules here that are happily interacting together. If this water molecule down here, the bottom one perhaps, is caffeinated like crazy or on steroids and it's moving around so quickly, it's going to just rip out of there. And so with high temperature, we're going to see that because that water molecule is going to just be moving faster, it's going to just rip itself out of that happy interaction. It can now just kind of do its own thing, where they'll have completely ripped apart. So if you think about it, just, caffeinating these molecules, they start becoming super jittery. They start moving very, very quickly. And as they do so, they just move apart. They're able to kind of rip themselves apart. And so we're going to see that that's going to be the reason for how we can explain the trend in boiling points we see. So, kind of in summary of this section, the more intermolecular forces you have, the more kinetic energy you need to break them. And therefore, the higher the temp needs to be, the more to break those to form a gas. Remember, gas molecules so far apart, they're not going to be interacting with each other. Remember that the force of interaction depends on how close they are. So if they're super far apart, they're not going to be interacting very well. So this is kind of the idea here. So the stronger your intermolecular forces are, the higher your boiling point will be. So strong IMFs means high boiling point. It also means high melting point as well, but that's a little bit harder to kind of understand, I think, than boiling. So we're going to see it's the same reason, though, and it's the same trend. So the higher your boiling point is, it's a result of strong intermolecular forces, things that are holding molecules together. If they didn't hold them together, they would have no reason to be together, right? And so they would just be flying around, zipping all over the place. And so we're going to see that methane if we look at their boiling points, the boiling points of these three compounds, methane's boiling point is negative 164, and water's is going to be 100. Let's look up ammonia's boiling point. Ammonia's boiling point is negative 33. And so even though their molar masses are similar, so if you want to think of things that are being heavy as harder to boil, that's true. But all of these are roughly the same. They're just slightly different, but not really a huge difference in their molar masses. But we see that because we have stronger intermolecular forces in water, we're going to see that it will boil at a higher temperature. If we look at hydrogen fluoride, or hydrofluoric acid, let's go ahead and look at its boiling point. Interestingly enough, HF boils at 18 degrees Celsius. Interesting stuff here, yes? I mean, methane, we know, has really just the London forces, that's it. But these other three have hydrogen bonds, don't they? They all have hydrogens bonded to nitrogen, oxygen, or fluorine. But we see that water is the victor here. Even though HF will have a molar mass of about 20, it still has a much lower boiling point than water. Why do we think that is? Why is water special? Well, O is very electronegative, and we have 2 hydrogen bonding units. So this is going to be kind of the winning combination. So even though fluorine is more electronegative, but only has 1 unit to hydrogen bond with. It only has 1 hydrogen, right? And nitrogen, on the other hand, is less electronegative, but it has 3 hydrogen bonding units. So, turns out that the winning combination is kind of your middle ground with really thick ink there. That's going to be the winning combination. What's also interesting is that oxygen, if we kind of draw these, we're going to see it's the lone pairs that are going to be interacting with the hydrogens on other molecules. So we're going to see that ammonia has 3 hydrogen bond kind of donor. 1, 2, and 3. 3 places it can donate a hydrogen bond, but only 1 place it can accept a hydrogen bond. Water, though, has 2 donors, 2 hydrogen to donate, and it also has 2 places it can accept 2 hydrogen bonds. So we can have 1 and 2 there. And if we look at HF, again, we're going to see it's the opposite case here. We'll have 3 places to accept, but only 1 to donate. And so, again, this is going to be kind of our magic thing. So for all of the reasons, oxygen being still very electronegative, but also having the kind of equal capacity to donate and accept hydrogen bonds, is going to be what really sets it apart. So with HF, yeah, you have a lot of accepting spots, but you don't have a lot of donors, right? So you're kind of limited by that. The same thing with ammonia. You have a lot of spot to donate, but you don't have a lot of spots to accept hydrogen bonds. And so if we're just looking at pure not solutions, but pure amounts of these, so a lot of ammonia molecules, they have, just relatively speaking, a few spaces to accept hydrogen bonds. So, as a result, just overall, because water can donate and accept equally, and has a very electronegative oxygen, it's going to kind of win out in having the strongest hydrogen bonds of all. So, just as a result within itself. And that's why we see this trend here. That's why water has the highest boiling point. It is because it's super electronegative, super small hydrogens, and it has 2 places to donate and accept hydrogens. So all of these waters can very happily interact with other water molecules. And it's really a very big reason that life can happen is because of water. So all life as we know it is based in water, right? All cells are mostly water. We as humans are mostly water as well. So super magic compound there. Very, very stable, very, very, very useful properties. Wow, I just feel like I've just gone on a rant about how wonderful water is. So, that's probably actually a good spot to end today. Understanding these forces. So tomorrow, I think we'll start with comparing what forces or identifying what forces different things can undergo. And then we'll talk about more properties. So boiling point is kind of the easiest one for us to tell and to look at in terms of trends. But there are other properties as well that we're going to talk about tomorrow. So we'll talk about surface tension and viscosity and all these other fun things. And we'll also talk about a 4th intermolecular force called the ion-dipole interaction. So, but I think that's enough for today. I think I've fried your brains enough for information that you're not even going to really start learning or deciding to learn until after your exam anyway. So, yeah, I think we're good for today. So, excuse me. I will see you tomorrow, I guess. Don't forget, you can start throwing questions in our review section area on Discord for Thursday. If any of you want to go over anything on Thursday for a review. If there are no questions, I won't do it. So it's all question-based. So if you want me to go over anything on Thursday, throw it up there. It doesn't have to be a specific question. You can say, hey, can we do another one where we talk about empirical formula or something? We can do that. So, alrighty. Well, with that, I'll see you tomorrow. We'll continue our exploration of Chapter 6 and Intermolecular Forces. Alrighty, take care.